BTEC Applied Science for Unit 2 Chemistry, Intermolecular Forces. Intermolecular forces. There's a spider walking on water. What's that got to do with it? We'll see in a bit. So, there are forces holding the molecules together. You know, we've talked a lot about covalent bonds, but there's also much weaker forces between the molecules. So this is the molecules attracting each other. Yeah, and that's what I'm talking about. So intermolecular forces producing intermolecular bonds. So what causes these forces and what are their effects? What difference do they make? Well, so we can call them van der Waals forces. The specification at the moment doesn't use that word. It just says we've got temporary dipole, induced dipole forces. They're called London dispersion forces. I'll explain this in a minute. And then you've got permanent dipole to permanent dipole forces. We know what dipoles are. And then an important example of that is hydrogen bonding. Now, this is a temporary dipole, okay? So basically, the electron is kind of buzzing around the nucleus, but it's not always perfectly like a sphere. It's like all over the place, like a blob, and at any point in time, you might find the electron a bit more on that side or a bit more on that side or a bit more up or whatever. So the electrons at any point in time, it's not always perfectly evenly distributed. At any instant in time, you might have a dipole. You might have one side of the atom or molecule is negative and the other side is positive. So it's a temporary dipole due to the electron bodding around like that. Now, therefore, for a very short time, what you get is the temporary dipole might affect electrons in another molecule, and that might cause another dipole. For example, if we look on this diagram here, this side of this molecule is negative. So if there's another molecule close to it, that's going to repel the electrons away, and then that end of that molecule will become positive. So you'll get another temporary dipole, and then the positives and the negatives will attract each other. So for a short time, there will be an attractive force between the molecules. So it's a temporary dipole attracting an induced temporary dipole. And these are called London dispersion forces. And I haven't got a clue why. They are very weak and they last for a very short time. Now, some molecules have a permanent dipole. Okay, we've talked a lot about dipoles, and that's due to the difference in electronegativities. If we look at this water molecule, excuse me, the water molecule has got a negative end around where the oxygen is, and then the hydrogen ends, if you like, are positive. And what will happen is that the positives and the negatives will attract each other. So this is a permanent dipole attraction. And there is a special case of permanent dipole, and that's called hydrogen bonds. And that's when you've got fluorine or oxygen or nitrogen bonding with hydrogen, and we get a large dipole and we get relatively strong bonds. Nowhere near as strong as covalent bonds, but as far as intermolecular forces go, these are pretty strong bonds. Okay, the attraction is therefore quite strong, and they are called hydrogen bonds. To give you an idea of the strength, so if a covalent bond, where the atoms share electrons, if we say that's 100, then hydrogen bonds, which are an example of permanent dipole-dipole, are about 10. Normally permanent dipole-dipole bonds about 5, and then going down to your London forces, your very, very weak temporary forces, we're talking about 1. So that gives you an idea of the strength of these bonds. Yes? Now, water. Hydrogen bonding is very, very important in water, and it has a lot of effect on the properties of water. Okay, and this is what I'm going to talk about here. Water has a high melting point and boiling point. Okay, why? Because to make it into a gas, or to go from a solid to a liquid, you're going to need energy to break the hydrogen bonds. Okay, and that means it's going to have a high melting point to go from ice to water, and a high boiling point. In fact, if it wasn't for hydrogen bonds, then at room temperature, which is about 20 degrees, water would actually be a gas. And it has been said that if it wasn't for hydrogen bonds, there wouldn't be life on Earth, because life on Earth, life needs water. So it affects the melting point and the boiling point, because you need more energy to break the bonds. Water is an excellent solvent, particularly for ionic compounds or substances which have polar molecules, because basically what happens is that the water molecules, imagine it's sodium chloride, the water molecules will bond to the sodium ions and the chloride ions and basically break them up and take them away and break down your big giant lattice of positive and negative ions. Yeah, so the water molecules form new bonds with other polar molecules or with ions, and that makes water a very, very, very good solvent. Now, surface tension. Surface tension is on the surface of water. The water molecules pulling together on the surface forms a skin. Okay, it's a bit like a balloon, you know, the outside of a balloon pulling sideways, yes, forms this skin. So much of a skin that insects can actually walk on water. And this is why we had Sammy the spider walking on water. So surface tension, yeah, is due to these hydrogen bonds, the water molecules pulling together. Another interesting thing is that the density of water is bigger than the density of ice. And one way of thinking about it is because in the water, the hydrogen bonds are pulling the molecules together, and that makes the water denser. Yes, and in ice, there are still hydrogen bonds, but they don't have the same effect because the particles are in fixed positions. So the hydrogen bonds pull the water molecules together, making it denser. And so water is denser than ice, and that's why ice floats, and that's why Percy the polar bear, they're standing on the ice having a look around. I don't know what he's looking for.